Hi folks, my name is Scott Mabin. I'm joined by my colleague Uri Sadel, and today we're going to talk about async Rust for embedded systems. So what are the goals of this presentation? We're going to explore how async Rust works, apply it to an embedded context. Finally, we'll show off a working application that leverages async Rust. First of all, why would you want to use async? It provides a mechanism for single-threaded concurrency, so being able to do multiple things with a single thread. And because of this property, it can run on a single stack, which is great for resource-constrained microcontrollers. We'll also have the ability to write asynchronous code that has similar ergonomics and readability as synchronous code, as we'll explore later in this presentation. So if you didn't see it already, I spoke a bit about Rust on espressive chips and mentioned async in the talk last year at the last DevCon, so check that out if you haven't. But in short, async in Rust adds two new keywords to the language, async and await. Async defines a block or a function to be asynchronous, and await defines yield points within that block or function to yield. So if we take this example function here, so we have an async function called sayHello, which takes a reference to a UR. And inside here, we set up the message to hello world, and we write the bytes out to the UR. At the point of this await call, the function pauses or yields here, where the hardware is actually transferring the bytes, and other things can run, or even go to sleep. Again, once the UART has finished transferring the bytes, we resume the function here, set up the next message, which is goodbye, and do the same thing again. We get the UART to write the bytes out and wait here until it's done. Let's think of a simple scenario to compare various approaches. So for example, reading the state of a button connected to a pin, and depending on the state of the button, turn the LED on or off. Let's look at a trivial busy loop example. So here we set up the two pins. We put the LED into an output mode, put the button into an input mode, and all we do is in a loop, repeatedly check the button state, and depending on the button state, either set the LED high or low. This is obviously very simple to implement and very easy to read, but it's very inefficient. We're using 100% of CPU power just checking that button state and changing the LED state. Let's try and leverage the hardware. Let's use some interrupts. So again, in this example, we define our two pins, but this time on the button, we have two additional calls to listen for the falling edge and the rising edge. We then enable the interrupt and then drop into the main loop. Before I explain the main loop, I'll also explain the two statics that we define at the top here. The first one is the button, which we'll need global access to the button in our interrupt handler, and a state, which represents the virtual state of the button, which we'll also need in our interrupt handler. When we drop into the loop, we check the virtual state of the button. And if it's set to high, we set the LED high, and if it's set to low, we set the LED to low, and then we sleep. And this sleep mode, in this specific case, will put the CPU in a mode where it's using less power until an interrupt occurs. So when someone presses the button, this is the interrupt handling code that will fire. So the hardware will run this code, and all we do in here is take our button, we clear the interrupt so we don't repeatedly call this interrupt over and over. We then check the state of the button, and then update our virtual state of the button inside here. So if the button was pressed, state is now true. If we come back here, we are at the sleeping line, and now the interrupts happen, it's been serviced, we wake up. We know that state's just been set to true because we pressed the button. So when we check it, we'll set the LED high and then go back to sleep. And then when someone releases the button, we wake up again, check the state, and it will now be low. We set it to low and go back to sleep. This is obviously much more efficient than the busy loop approach. We now have the option to do other things or sleep in this case. However, it's hard to follow the program flow um, of execution. Just then, as I was explaining it, I had to go back and forth between the main loop code and the interrupt handler. It's quite hard to understand what's going on. Let's look at an async example. So first off, big difference is main is now an async function. Again, we define our 2 pins and then drop into the loop. Now the main loop looks a little bit different. So we have a select statement, which select will basically wait for 2 things to happen and tell you which one happens first. So here we're waiting for either the wait for rising edge event to happen or the wait for falling edge to happen here. As soon as we call await, this function freezes until one of these events resolves. So this means that we can either go to sleep, run other tasks whilst this is waiting to happen. So in the case where the button is pressed, the wait for rising edge event will resolve, and then we'll execute the first match arm of this match statement, which will set the LED high. We'll go background into the loop and wait for the 2 events once more. So when the pin is released, the falling edge, when the button is released, the falling edge will resolve and we'll execute the second one, turning off the LED. Structurally, the async example was very similar to the busy loop, but with async, each await point allows the CPU to do something else or even save power. So essentially, we get the best of both worlds. We get the ergonomics of the busy loop with the efficiency of the interrupt example. And behind the scenes, async will actually use interrupts, but it's hidden away, so the users don't have to worry about that. How does async actually work? Well, you can only await something that implements the future trait, and the future trait has one method, poll, which returns either poll ready if the asynchronous operation is completed, or poll pending if it needs to be polled again later. This is what the future trait looks like in Rust code. Async's relationship with future is an important one to point out because async functions are actually compiled down to state machines by the compiler, which implement the future trait. And this means that the future trait is the building block for any asynchronous operation in Rust. This is important to note because throughout this talk, I'm going to use future and async somewhat in the same context. And basically, every async function is a future, and other things can be futures as well if you implement them manually. When should you poll a future? You could just poll them continuously. Much like the busy loop example, we could just sit there in a loop and wait until a future returns poll ready. However, this is not very efficient, as we use 100% of CPU, just like the busy loop example. And given that we are going to the effort of implementing the future trait for our types or using async functions, we'd like to do other things whilst also waiting for one thing to complete. This is where the waker concept is introduced. Waker is something that can be used to signal that a future should be polled again. And waking a waker can happen from anywhere. Some examples being an interrupt handler, like in our button and LED example from earlier, a callback function, or just another function. This is a pseudocode socket read implementation of the future trait. I'm just showing you this to give you a idea of the life cycle of a future. When a future is created and executed, the poll method will be called once. Inside this poll method, we check, do we have data to read? If we do, great, we can early exit and return poll ready with the data. However, However, if we don't, we then need to set up some mechanism called poll on this feature again in the future. So this set readable callback registers a waker, and behind the scenes in this pseudocode implementation, it could be a operating system callback to say, yeah, there's data in the socket. And once we've done that, we return poll pending. So when the OS actually runs that callback to say there's data in the socket, poll will be called again. We then check if we have data, and then we return poll ready. So how do we actually run futures? We've covered how they work, but where do poll pending futures actually yield to? They yield back to something called the executor. And the executor is just a mechanism to run futures. It handles the response to wake events and then polls the relevant future again. Executor is a general term. There's no trait or contract for them in Rust, and they can be implemented in various different ways and have various different features and limitations. One popular executor for embedded systems is the Embassy executor from the Embassy project. It aims to provide not just an executor, but a collection of tools and utilities to create effective async applications. Usually the top level future is called a task. Within a task, many futures may be awaited, but the top level one, the one that is spawned on the executor initially, is colloquially known as a task. In Embassy, tasks are statically allocated to avoid the need of an allocator. And fortunately, the Embassy executor task macro will take care of this for us, so we don't have to size up our statics or anything like that. Tasks are allowed to have infinite loops, much like a traditional RTOS task, but must contain at least one await point to avoid blocking other tasks. I'll now hand over to my colleague Uri Sadel, who's going to walk through building an IoT temperature sensing data logger that leverages async.
So hello everyone, my name is Uri Sadel, and I would like to go through our hello world kind of example for IoT. But before that, I would like to talk briefly about what is bare metal or no STD. Well, by default, each Rust program is compiled or linked with a standard library or STD. And for some cases, especially embedded development or kernel development, we sometimes want to use no STD. So how we can actually tell Rust compiler that we don't want to use standard library, but we want to use something else, which is called the core library. Core library is like a collection of basic functionalities and is a subset of the standard library. And we can do that with attribute or macro attribute no STD, which is the first line. So with this, it's first step for bare metal program, and then we have to also specify where our program should start running, and we can do that with no main and entry macro. With entry macro, we basically set where the entry point to our program is, and because when we do not have standard library or operating system, we have to do these things manually by ourselves. So that's why we have to set these things. And also we have to set panic handler. Panic in Rust is when unrecoverable error occurs. So we have to specify what must be done when such event occurs. So now about the demo. Our demo consists of 3 steps. The first step is to initialize and connect to i5. Second step is to initialize and create MQTT client and connect to the broker. And the final step is to initialize temperature sensor, get temperature, and send it to the MQTT via Wi-Fi. What we need, we use the Rust board or C3, ESP32 C3 board, and BMP 180 pressure sensor. Okay, so now we are in the Visual Studio Code. And as we can see, the first two lines are, as I showed you 2 slides ago, no std and no main. So basically, we are kind of ready with bare metal program. Then we here on the second window, we have the entry macro. So we are specifying explicitly specifying where should our program start executing. And also we are using our own panic handler, which is ESP backtrace. Like usually this comes as a standalone or external crate. So regarding the code, we have a bunch of imports here. These ones are from hardware abstraction layer and are related for clocks, I2C, and stuff like that, like the basic hardware peripherals on the chip. Then we have this imports for ESP Wi-Fi, some configuration, like Wi-Fi device, and so on. Same for Embassy Executor and async stuff. And then we have our sensor and Rust MQTT. So I will continue now with main function. So at this point, like this thing will be like executed like in blocking fashion. So for now, it's still no async application. So we firstly initialize the clock. We are using the maximal frequency for the C3, which is 160 megahertz. Then we are disabling watchdogs. Then we are initializing Wi-Fi, radio, so on, initializing Embassy, starting Wi-Fi, and initializing I2C, because BMP180 sensor is communicating via with C3 chip via I2C communication protocol, and stack, enabling interrupts for I2C. And at this point, we are initializing and starting Embassy, and this part is becoming async. In our demo, we have 3 tasks, and I will go to them and walk through them. So the first task is regarding Wi-Fi. So first, we are checking the state of ESP Wi-Fi. If we are connected, then we just like going through this and waiting for some disconnected state. For example, if our Wi-Fi router stopped working and so on. But on the first run, we skip this match and we continue with this. If Wi-Fi started correctly, we can send Wi-Fi credentials as SSID and password that we have to set as environment variables here before running the code. And so we have credentials ready. We can continue setting configuration, and we can finally start and connect to the Wi-Fi. If everything goes okay, we should be ready with Wi-Fi. Second task, it's like background task or helper task, which is checking for packets. And when new packets arise, it and process them. It's basically a wrapper of small TCP. And last async task, which is our main basically task. We are checking or waiting until Wi-Fi is connected. Then we are waiting for DHCP IP address, creating a socket, and we are using public MQTT broker by HiMQ. So this is the host address. So we want to get an IP address from this address. If we get the IP address, we can create a remote endpoint. We are using port 1883, and we can finally establish the connection and create a configuration for MQTT and connect and subscribe to the MQTT broker. If everything is ready, we should be communicating with MQTT broker, and the last step is to create and initialize BMP sensor, start measurement, and start publishing temperature to the MQTT broker. So right now, I will try to run the code. So now I would like to flash the actual code and show you how it should look like. Okay. We are getting some logs. We are waiting for Wi-Fi, for IP address. Sometimes it takes a little bit more time. Okay, we finally got IP address, and now we are getting the temperature. So now I can go to the public HiveQ MQTT broker, and we can connect from here, and we should get the temperature data sent here. So we'll create the connection. We'll add the topic. I put some random name for the topic, so we are the only ones getting messages here, and we are good. And we are getting the temperature. If I touch the sensor, the temperature should go up. Yes, 28, 30, and so on. Okay, so that's the demo I wanted to show you. Okay, so this is the end of our talk. Here we have some links which are related to our talk. Thank you for listening, thank you for watching, and if you have any questions, please feel free to write to the chat or ask us during live Q&A. Thank you very much.